So as we are discussing the 4D bioprinting based on biomaterials, now this is another study where two different biomaterials like AMA or HAMA and AAMA or HAMA, like hyaluronic acid, acrylic acid, methacrylate, and hyaluronic acid. So these two materials are used to prepare a two different layer structures. But the thing is, these two different materials have different swelling ratio. Because of that, and because of that, the structure will get folded. So now here, this in this paper, please go through this literature. You will understand the work. Also, you can read the work in details. Where you see they have prepared the structures on a glass bed, printed two different materials, two different layers are printed. Then they have, because these are methacrylate groups are added, so these materials are photosensitive materials. So then they have used a green light to cross-link the material, where this film-like structures they have fabricated to a bilayer film-like structure they have fabricated, and then they have radiation to this thing to fabricate the structures. And then what happens, then after the cross-linking, because the cross-linking, two different materials having two different cross-linking density, sorry, having different swelling ratio here, and then when these materials were put into water or PBS, then they have just folded, the materials get folded, and we get a tube-like structures. So this, in this particular study, they have used this concept of 4D bioprinting of biomaterials, uh, responsive biomaterials, where they, due to these materials, due to the water absorption or swelling of the materials, there can be a change in shape. So that's why a folding into tube-like structure can be get from a planar structures by only introducing water. So that's the this is a very important work. Please go through the literature for better understanding. Now there are a few more studies where what they have done, they have uh, used the concept of cellular self-assembly or self-accommodating process, by which the changes, post-printing changes, can happen due to this self-assembly of cellular self-assembly process. Here, please go through this two literature where they have uh, shown this possibility here, these two papers, where the first one, they have used a they have used smooth muscle cells to print vascular tissue construct. But here they have not printed actually the vascular tissue construct, they have printed the cells in the discrete cell droplets, right? Like as I have shown in the earlier slides, that the cell, when the same cell droplets can be patterned discretely in a, suppose in a spherical pattern, then what will happen, upon time, these droplets will merge with each other, the cells will get assembled with each other, they will form the whole tube structure, and then we can, in that case, we can get a the whole a different a tube like a spherical tissue like construct. So depending upon our design or our interest, we can get different types of structures we can print within the same concept. So this is a very important study. We please go through this latest literature, where you can get the spheroid, cellular spheroid. They granularly merged with each other to form a ring-like vascular graft. In this work, they have also shown that suppose if we print to do the adjacent drops were printed with different cell types. Like suppose one particular smooth muscle cell and fibroblast, again smooth muscle, again fibroblast. Like if I alter this cell, the self-assembly process will happen, but the cells, suppose smooth muscle cells and fibroblast cells, they can maintain their positions. They will not get merged. They will not get all mixed up. So, and if we print two different, suppose two concentric rings with two different cell types, then also the cells can able to maintain their shape. They are not they are not getting mixed with each other. So this work, in this work, they have particularly shown how cellular self-assembly can be used for bioprinting of a, suppose, a ring like vascular construct. In the second work, there they have used in this work, actually they have used a template based approach, where agarose rods agarose rods are used as a template. This agarose, the important thing is this agarose is can be liquid at high temperature. So what happens? They have printed these agarose rods, and then in between the agarose rod, they have also printed this skin fibroblast spheroids. The skin fibroblast spheroids were prepared, and those skin fibroblast spheroids were printed in between the agarose rods, and then they allowed these spheroids to self-assemble with each other, and by this way we can get a whole fibroblast rods in between the agarose rods. Suppose we put the in the agarose rods, and in between we suppose we print the skin spheroids, fibrous spheroids again in between one agarose rod template. Suppose we print a ring-like structures like this, a tube-like structures of with the skin fibrous spheroids within this agarose rod templates. Then also we can get a then in that also with that we also we can get a tube-like construct, because this agarose rod templates, they will provide the support at the beginning, but this spheroids they will assemble. So the self assembly of the cellular self assembly of this will happen for the spheroids, and then we can get the vascular tube-like constructs. So these two works where the cellular self assembly can be, how the cellular self assembly can be used for 4D bioprinting, that those were presented in this two work. There is another work where they have, suppose we printed a vasculature. Here in vasculature bioprinting, we have discussed how the vasculature can be printed, the tube-like structure can be printed with the with this material called a sacrificial material concept, like sacrificial template concept. Suppose we printed with the sacrificial template, we print a tube-like structures. Then if when we take out the sacrificial material, we get a lumen-like structures. Now within the lumen, when we put the endothelial cells within the lumen, what will happen? These endothelial cells will go and bind to the lumen, and then they will then in that way also we can get a vascular tube-like construct. Here, think about the thing before. First, there is nothing within the lumen, only the lumen-like structure, where with the only the template sector with the sacrificial material is present. Now, after that, by some means, suppose we remove the sacrificial material, that can be by changing temperature or by washing with the water. The sacrificial material, now the sacrificial material, we get a lumen-like structure, but there is no vascular tissue-like structure construct till then. Then when we put the endothelial cells within that construct, then it will be a vascular tube-like construct. So this also can qualify for 4D bioprinting, because here the design is such that we have designed the vascular construct in a particular way. Then we put the cells within the vascular construct. The cells form a monolayer. So that is not present at the beginning, but after post printing, that monolayer formed upon perfusing endothelial cells within the construct, and by this way also we can get a vascular tube-like constructs. So this so different there are some works in this particular domain where the maturation of the tissue construct can be also used for 4D bioprinting. So 4D bioprinting based tissue maturation can also be one particular strategy for 4D for developing novel tissue constructs. So please go through this literature. So there are more and more. There are many more literatures you can get. So, and I will encourage, or I will suggest, please go through the literature for better understanding. Due to the time, I have not included many of the such interesting studies, but I have given some literatures. Now, as we have already discussed, this 4D bioprinting can be used for different biomedical applications. So one such area is tissue engineering, where this can be used for developing tissue engineering constructs, like as vascularized tissue construct is one important area, where how to generate vasculature, as I have discussed in the earlier slides. Just like that, how we can generate a vascular tube-like structures with either by a sacrificial template concept, or by using another, by putting the cells in a particular fashion, so that then the self assembly process happens. So vascularized tissue construct, for vascularized tissue 4D bioprinting can be employed or can be used to come up with a vascularized tissue construct, novel vascularized tissue constructs. So that is one particular tissue engineering area. Another thing is the hard tissue. Suppose for bone tissue engineering also, there are some studies where 4D bioprinting has been used for maturation, cellular maturation or construct maturation, and then further development of the whole vascular, all whole bone tissue. So and this is just two examples, but there are many more where 40 bioprinting can be well for tissue engineering. And one important thing is, if you see in the native tissue, or in our human body, the different organs, different tissues, they are under continuous turnover. That means the tissue is continuously getting remodeled and modeled. So this is the tissue is getting changed all the time, and it is getting remodeled. So 4D bioprinting concept is one such that can accommodate these changes, because here we are talking about these changes, that is the programmable changes that can happen over time. So that's why 4D bioprinting is a very important concept for, and it can very well suit for tissue engineering application. Similarly, for drug delivery application, whenever we are talking about spatiotemporal distribution or spatiotemporal controlled release of the drug, there 4D bioprinting can play a big role there, because it here 4D bioprinting relies on self-folding and unfolding to encapsulate drugs or cells, and also their release. So what happens, suppose if we control the when we control the self-folding. Now, when the device is getting folded in that physiological environment, no, sorry, in our fabrication environment, where suppose in that case, if we include some drugs or cells, the drugs or cells will get encapsulated within this device, within the device, due to this thing. Again, if we put them in the physiological condition, what will happen? That device can again unfold, and the drugs or cells can get released. And this can happen, suppose this can happen at particular pH, this can also happen at particular temperature. So these things are very important for controlling the drug, for modulating drug delivery, for cell delivery. So all these things, so for that's why for drug delivery applications also, bioprinting can play a big role. And there are many such studies where this kind of things, by protobioprinting has been used for Protobioprinting has been used for to suit a particular drug delivery applications. Now, if you see in literature, this protobioprinting concept is very new. It has come only a few years back. Before that, people have worked on many such concepts, or many such technologies or processes, where they have used, or they had used, some programmable change or design or process, but they have not explicitly mentioned 4D bioprinting in their work. But here, but now, when we look back those literature, we can always find that yes, those research works or those literatures can also be called as 4D bioprinting, or can also be qualified as 4D bioprinting, because they have used such concepts. So that's why, though some literature, they have not explicitly mentioned the work, but please go through the literature whatever I have given you. There are also two review articles are there they have explicitly mentioned the earlier work, like these two works. Here they have not, in these two work, they have never mentioned about 4D bioprinting words. But now, because they have used this concept, 4D bioprinting concept, then that's why they are qualified to be called as a 4D bioprinting techniques. So that's what happens. Now, if you see, go to literature, please read the literature, and you will find more and more studies that can be qualified, and that can be one exercise that can be done by you. That what are the different research works that can be for that can will qualify for the bioprinting. Now let us discuss 4D about the limitation of the and future scope of 4D bioprinting. Now, though 4D bioprinting technology is is excellent, well suited, and has very high potential for tissue engineering as well as drug delivery, but there are certain limitations, and we need to overcome those limitations for wide applicability, wide use, or widespread use of this technique, or better applications. Like suppose in 4D bioprinting, mostly you rely on responsive materials. If you see, we have only very few limited responsive materials where it can respond. Suppose it can respond to either temperature or pH, magnetic field or respond to water, like swelling, right? So, but we have limited number of materials to do that. So this, and because of that, there is a interest to find to explore or invent new materials that can be applied for 4D bioprinting. So this is on future scope where more and more, if we can actually invent or if we can design more and more biomaterials or smart biomaterials that can respond to certain external stimulus, that can be very well, that can be very good for 4D bioprinting. Now, other important thing is most of the smart biomaterials or responsive biomaterials, they only respond to one kind of stimulus. But that is not good, because if you see in a human body, it's a very complicated microenvironment where this all the different types of cells or materials, they are under multiple types of stimulus like mechanical pressure, electrical flow, electrical signals, magnetic field, temperature, pH. Again, different types of stimulus are there. Stimuli are there present. So in human body, it's a complicated microenvironment, and that are mostly stabilized by multiple regulatory processes such as neuroregulation, self-regulation, and humoral regulation. Right? And because of this, our human body can work because of these different types of regulatory process, and that's why there is a balance between these two, and that's the body can function in a better way. So with only if certain biometers, if they can respond into one kind of stimulus, that is not good. That is nowhere it can be comparable, or it can be used for human applications, because we don't know what will happen if we put that into the body, and what will happen to the it if it encounter other type of stimulus. So that's why we need to come up with a material that can respond to different types of stimulus, and that then only it can replicate the human body in a true sense, and also it can be very well used for 4D bioprinting application. The other thing is 4D bioprinting materials are capable of self-deforming in response to multiple physiological responses, are favorable for biomedical applications. So that's why this we need different other types of material that can respond to different physiological signals, and definitely that will be favored for biomedical applications. So what can be done actually in in addition to discovering or inventing new materials, the if we can program, if we can design the existing material to respond to certain stimulus, that can be very well used, and that can be the task for the future. So where if we can use whatever the existing materials are there, if we can use them, if we program them, if we can design them in certain way so that they respond to different types of stimulus, and then that can be definitely used for 3D bioprinting application or for 4D bioprinting applications. Now, another limitation is the majority of the 4D bioprinted constructs are limited to simple deformations such as folding, unfolding, or self-organization. We have also seen few of the examples where either these research were mostly this type of works. What they rely on self-folding or unfolding upon single stimulus, or self-organization. So that deformation is very simple in nature. Either there is maybe let's up some shape change or some change in size. So that can happen. But in our body, mostly these changes in our body, whatever the changes happen, mostly these are happen at certain location, very precisely at certain locations or certain in a spatio-temporal manner, right? So that if we can replicate, then that can be useful, that can well suited for biomedical applications. Like so, that's a precise control of the spatio-temporal evolution of the printed objects. That is challenging, but that is very much required. Right? So if we can control the spatio-temporal variation or evolution within the body, that can be very well. If that can be controlled, then it can be very well used for biomedical application. So here the key is the spatio-temporal evolution, because the body is evolved over time. So if we can come up with some material that there, if where the changes can happen spatio-temporal manner, that can be very well used, and that is required. Now that's why controlling the bioprinted constructs on a micro scale or localized control is very much required, and the change in their shape, orientation, and functional or functionality, which could be achieved by adjusting external stimulus or by self assembly. So, if we can control, here again the key word is the controlling their changes in micro scale. So, if we can control the properties or if we can control the changes, or if we design the changes of that of those by printed for the 3D printed structures in a micro scale, suppose the localized, even a localized, suppose in a whole printed construct, can we control the property in that particular special control in a particular location? If we can do that, then only we can able to come up with the material, and we can actually truly mimic the in our biological systems, and that can give us a better understanding or give us better mimicking property, or that is can give us better suitability for biomedical applications. So other thing is also most of the bioprinting 3D bioprinting process where the resolution is on the in the macro scale, like even like hundreds of microns or millimeter scale resolution. With that, we cannot prepare a structure to achieve highly accurate spatiotemporal control geometry. Like we cannot, we can suppose we printed a construct. If we are not, suppose if we want to control the, if we want to change that thing, change the properties of the structure, or if you want to bring that changes, that post printing changes in a micro scale, and if our resolution is not that great, we cannot able to match that. That's why improving the printing resolution is another task, and by this way only we can control the, or you can achieve highly accurate spatiotemporal control changes can be achieved. So these are the for some of the limitations and future scope. Again, the other thing is when we work with cellular maturation, right? So then how, if we can control the cellular alignment, that can give us better mimics of the in vivo tissues, like control over the cellular alignment, that can give us better clue and better strategy for controlling the for mimicking the in vitro in vivo tissues. So that is also when we work on cell maturation. We have seen some of the works like where we have seen some of the works where so when we have discussed various types of various strategies based on cellular maturation, where I have seen that the if we can control this the cellular maturation process, like where if we culture the cells in the construct, and then if we can control the how the way cells will behave, or the way the cells will mature, the construct will mature, then we can have a better mimicking structures. So there's cellular alignment. That is one strategy. The cellular, suppose if we can control the cellular alignment, so that can suit, but one particular some particular tissue construct like a muscle, cardiac smooth muscle construct, or maybe the tendon, ligament, muscle, or where the suppose the cells are present in an aligned way. If we can control that one, that can be one way to mimic the in vivo tissue. And 4D bioprinting, in 4D bioprinting, maybe we can work on that, how we can design that kind of construct where the cellular alignment can be induced, and then it can work in that way. Suppose in case of blood vessels, like for instance, in the blood vessels, as we have earlier discussed, that comprises three layers like the tunica intima, tunica media, and adventitia. Like where the innermost layer is the intima, where endothelial cells lining is present, then the smooth muscle, and then fibrous cells are present. Right now, if we can control the cellular orientation in different locations, like suppose if we control the smooth muscle orientation in the middle layer, and the endothelial lining in the inner layer. Now, if we can control the cellular orientation at different layers, then it can closely resemble the native vessel. And then if we can design our tissue construct in 3D printing in such a way so that the smooth muscle cell will get aligned in that particular in the middle layer where the means that uh, tunica media or the muscle layer, and then the endothelial cells, they will form a monolayer in the tunica intima, and then the fibrous cells also will be present on the outer layer. So this kind of construct where the cellular orientation alignment is very much important to achieve that blood vessel structures, that can be, if we can control that, if we can do that, and if we can get, if we can, with 3D bioprinting, if we can do that, and this, then this changes how the cells grow, and then when they grow, and then they will get this kind of particular, this 3-layered blood vessel structures, that can be the ultimate for 4D bioprinting applications. So with 4D bioprinting, there's a huge prospect, but these are the some limitations, and probably we need to work on these things so that we can able to use this technology for better, so to come up with better strategies, to come up with better mimicking structures, or biomimicking structures, so that finally we will to get the finally functional human tissues and organs. So for body bioprinting is a huge, is a very good technology in that particular direction, but we need to work more on these things. So these are some of the bottlenecks, but we need to overcome these challenges. Now let us again revisit the definition. We have started with the 4D bioprinting definition, when we have discussed what is 4D bioprinting, what are the things, what are the most important features of 4D bioprinting, and what are the technologies that we can call them 4D bioprinting. Now again, if we read this, so I've taken this from this reference. It is the construction of individual multimaterial printed objects from either living or preliminary substrates for medical or biotechnology applications. So this is at first, so they are telling about the constructs of individual multimaterial printed objects. So where multimaterial can be present from either living or preliminary substrate. So that can be either living, the cells can be there, or can be only biomaterials for medical and biotechnology applications, when they are specifically engineered to respond in anticipated ways to user demands or a changing environment by self-actuated morphogenesis, cellular differentiation, tissue patterning, defined biological characteristic alteration, or functionality development. So these all things can, here this definition is inclusive, and it can be used for, and here this is an inclusive definition where all the things whatever we have discussed, everything is put together, then we get this definition. So here it talks about multimaterial printed objects that we have seen, where bilayer structures or trilayer structures can be printed. Cells can also be included within this, and also we say like primitive substrate material. And it is mostly for medical and biomedical applications, biotechnological applications. That's why it's a 4D bioprinting. And these are specifically engineered to respond in an anticipated ways, or in a programmable way to user demands. So whenever based on our requirement, we can actually engineer them, or we can design them to respond to certain way, so that that change, so it or that environment, due to the environment change also possible, changing environment is possible by self-actuated morphogenesis, cellular differences, and tissue patterning, and defined biological characteristic alteration or functional development. So all these things. So in the last part of the sentence, and where this 4D bioprinting based on maturation, tissue maturation, is also covered within this definition. So this definition is inclusive, and here this is the whole, this is actually, this tells about the whole bioprinting, whole 4D bioprinting concept. So this thing. So with this, we'll come to the end of the 4D bioprinting concept. I've given few literatures with my slides, example, few references. Please go through the references. Thank you very much for attending this lecture.